Hello friends and welcome back. In this quick, I hope, video, we will be briefly talking about this, the juxtaposition or the difference between equilibrium, which is what we've talked about this week, so statics, and stability, which is a related but slightly different and subtly different concept. And so we defined equilibrium, the conditions for equilibrium, where the net force acting on an object is 0 and the net torque acting on an object is 0. And so in principle, if these conditions are maintained, then this implies no acceleration and in particular no acceleration of the center of mass and no rotation or no torsion. Okay, and this is all, you know, nice and great, and we practice a lot, and you will practice even further. But the reality of nature is that there's a little more to this story, and the reason is that you can never really forever maintain perfect equilibrium. There's no such thing as perfect equilibrium. And the reason is that if you look microscopically, now that we have, well, we know more about nature, you know, even if you take an object and you see that all the forces are balanced and the torque and the net torque is 0, if you zoom in with a magnifying glass, you will see molecules. And these molecules have some random thermal motion, for example. And there's no way for every single one of them to precisely add up where the forces are forever and ever exactly 0 and the torque is exactly 0. Not to mention, you know, if you look at quantum mechanics, there's even quantum uncertainties relating to the position and momenta of these particles. So there's no such thing as real perfect equilibrium. And so then a very meaningful question is, okay, what happens to an object or to a system when I deviate ever so slightly from equilibrium? So what happens when there are some perturbations from equilibrium? And there's essentially 4 different types of responses of a system to small perturbations from equilibrium, and these are as follows. Let me list them. Let me shrink this. I'll put this somewhere up here. Okay. Type 1 is stable. A system may be stable to small perturbations. This means that perturbations from equilibrium tend to go back and return to the equilibrium point. They tend to be, the equilibrium is brought back, perturbation is brought back towards the equilibrium point. An example would be if you take a marble and that is at the bottom of a round bowl. If you imagine to slightly displace this marble, it will go back and forth maybe a little bit before slowing down and stopping, but these perturbations that you've applied, they tend to be brought back towards the bottom of the bowl and to go back to equilibrium. The opposite case is of an unstable equilibrium. So stable equilibrium, an unstable equilibrium, where instead perturbations grow and keep growing. And this is, for example, if you place a marble at the top of a hill, of a very smooth hill, and you imagine to right at the very top balanced so that in principle it's there in equilibrium, but if you slightly displace it, it will start rolling down the hill. So that's instability or unstable equilibrium. A third kind is metastable. And this is where basically small perturbation, very small perturbations are stable, but the system may be unstable for slightly larger, perturbations. A case would be, for example, if you have a marble in a shallow hole, but at the top of a steep hill, then as long as the perturbations are so small that the marble stays in the little hole, then you're good. Something like, actually, I'll draw a diagram just now, but well, let me just illustrate this point. Imagine that the marble is in a landscape like this, on a hill, and if you perturb it so that it stays in this little shallow trough, then you're good. But as long as the perturbation is just large enough to push the marble down this hill, then it becomes unstable. This is a metastable equilibrium. Another more generic way of talking about metastability is where it's sort of locally stable, but there's another place that would be absolutely stable, more stable than that. And last but not least, although it's the least interesting of the four, it's a neutral equilibrium, where perturbations kind of don't do anything. Perturbations stay where they are. Where they are. And this would be a marble in a perfectly flat tabletop, for example, on a perfectly flat tabletop. If you slightly displace it, it's not going to go back where it came from. It's not going to keep growing perturbation indefinitely. It's simply going to stay there where it is. And armed with the language of potential and potential energy, I want to draw sort of 4 examples for that apply not just to, a marble on a certain landscape, in a certain landscape, but to more in general, like anything that lives, objects that that have a certain potential energy of a certain shape, and we can discuss the type of equilibrium that they're in. So, classic example of a parabola, for example, or something like this, this would be stable equilibrium. So remember that when this is potential energy, when du over dx equals 0 implies that force equals 0. Remember that there's this relationship between force is minus du over dx, and so it's also 0 at this point. So force equals 0 means equilibrium, but stability has to do with the shape of the potential in that point. So if the potential is shaped, has this type of convexity, then you're stable, because small perturbations will tend to go back to the stable equilibrium point. Vice versa, a shape like this would be unstable, because perturbations, if I slightly displace from equilibrium, will tend to grow and to move. Actually, let me draw the arrows horizontally, because that's will move in this direction or in this direction at larger values of x. Metastability would be something like I drew before, something like a shallow hole, and then, or maybe let me draw it like this. See, if I'm in this position, this is metastable, because again, small perturbations would be somewhat stable. It would stay in here, But if I get past this distance, then perturbations would grow, and eventually this, for example, would be instead an actually stable equilibrium. And last, and perhaps least, neutral equilibrium is one where I'm simply flat. Again, perturbations, if I slightly displace my point and I bring it here, it's not going to go back to where it was at the start. It's not going to keep going. It's simply going to stay there. So again, equilibrium means no forces and no torque, but perfect equilibrium is not achievable in real nature. And so then studying and understanding the stability of a system and what determines the stability of the system is really crucial to be able to predict the behavior of the system in real life, not just as a mathematical abstraction, but in the actual real world applications. So I'll try to help you practice a little bit on this type of ideas, but for now, thank you so much for watching, and I'll see you soon.